So constant rate of change, this comes up in Math 7, and you're given charts, and you have to figure out where the constant is. And this came up when you did unit rate. Do you remember unit rate?
Yeah, I do.
So you had a unit rate, and a unit rate was any number over 1, remember? Over 1?
No.
The unit rate. Okay? And that we did when we did proportions and ratios, and we were setting up things and we're finding a unit rate. Okay? So this is a slight bit of review, but mostly new stuff. So we have this linear relationship. And in your book, it has a real long definition, but this is really all it is. It just means that you're going to have a straight line on a graph. Okay? Yeah. So a straight line graph, that means linear, like think line, linear, right? All right. It'll come back.
You sure?
It sure did.
We ain't got it.
You forgot to put the light on.
Yeah, you're right.
Projector.
Right.
Do you want me to shut them off again?
Want me to turn it on?
I'll turn it on.
Video's ruined.
Recording, it's fine. It's more entertaining that way.
This is how we work.
All right, here we go.
Miss Monroe's
We're
class.
too loud for this.
No, we're
Okay.
not.
So we have a constant, linear, straight line. Think straight line is going to be constant. A straight line means it's changing the same each time, right? It's going up at the same rate or maybe going down at the same rate. So that's our linear. And then we have this constant rate of change. And here's the definition for constant rate of change. Again, your book is more wordy than this, but basically it's the rate of change between 2 points on a linear graph. So you have 2 points on a graph. And this is the rate between the 2 points. It's how the points are changing or how the graph is changing. That's our constant. Do you guys recall when you started learning graphing and you learned x, y coordinates? Remember this?
Yeah.
So you have these x, y coordinates, and it's always x comma y, and you always graph the x like this, right? So x is the horizontal, y is the vertical. Remember this? So you would go out, say this was 2 comma 4, you would go over 2 and up 4 and put a dot. That's a point. And if I wanted to do another one, I could do it there and connect the dots, and now I have some sort of slope, right? Okay? So this is review. This is some elementary school stuff. And then 7th grade, we did a bit more. Okay? But that's what they're talking about when they have the 2 points on a line. All right, so we're given this in tables in Math 7. And we have to find a constant. The tables on the left are your x values or your input. On the right is your y value or your output. These are words that you may have heard before. Input, output, x, y, values, things like that. So on the left, we have 3, 6, 9, and 12. And on the y, on the right, we have 170, 140, 110, and 80. And then I put little numbers on the outside with arrows, and that just shows you how it's changing, okay? This one's going up 3, and this one's going down 30. It just shows you the change right there. So write all that down, and then I'll talk about the other stuff that's up there. That might be real new to you. going on here? We have different things, right? We have this chart, which is like a table. We've seen these tables. In Math 7, this is how we found the constant. We just took this number over here and put it over that number. So we took the change here, like negative 30, and put it over 3. And that's what's going on. So right here, this little triangle means delta in Greek, and it means change in math, or difference, okay? So we have the change in y over the change in x. That's the negative 30 over the 3, which simplifies to negative 10, okay? And it's always y over x, and then the constant rate is negative 10. So that means this graph, if I'm going to graph it, it's going to be going down at a rate of negative 10. Question, Emma?
Yeah, why is there like, what's the triangle thing?
That just means change.
Yeah, okay.
Yeah?
Wait, we're doing this, are we gonna write it exactly like that?
Pretty much, yes. Some of them. Okay? All right, so sometimes the chart is sideways like this. It's more of a horizontal. And I don't want you to be confused, so I did an example like that too. Because when it's horizontal, the x is the top values and the y are the bottom values. This happens to be a chart of Celsius and Fahrenheit. So we have Celsius, Fahrenheit, and these are actual temperatures. Like when it's 0 Celsius, it's 32 Fahrenheit. Okay? So remember on these ones, you'll have the x values are the top, the y values are the bottom. We still do the y over the x though. So when you guys get to this point in science, either this year or next year, and they'll ask you to convert, they'll say convert Celsius to Fahrenheit or Fahrenheit to Celsius, and the formula for conversion will actually have the 9/5 in it. The 9/5. So you'll see that again. That'll come back up pretty soon. I can't remember if it's 8th grade or 9th grade science, but it does happen. So Celsius is in the metric system. Has anyone ever lived in a metric system country or traveled to one? You have? Taylor, which one?
I used to live in Europe.
Europe is all metric. Good. So you know Celsius. And Mary?
I've been to Armenia.
And they're metric. And who else had their hand up? Jose? Did you?
Yeah, we visited Europe.
Europe? Any other countries that you've been to? Grayson?
America.
Uh-huh. Standard system. Anyone else been to another country like Canada where they do this in Canada?
Canada.
Okay. Do they do this in Mexico?
No.
No one
Yes.
knows.
They do?
Well, depending.
They do this in Mexico.
Don't they do it everywhere but here?
They do it everywhere but here. And here's the history behind it.
For America.
And there's 2 different ones too. I'm telling you.
Okay, so what happened was the Americans wanted to be different when they left Europe, right? So they came up with their own system, right? Which is feet and inches and stuff. And then they used that. And then I think like 100 years ago or something, someone wanted to change it back because it's a lot easier to do metric. It's all in tens, hundreds, and thousands. But then the football players didn't like that because then they had to change the field because it's in yards. That's what I heard. I don't know if it's true. But that's one of the stories. I'm sure there's plenty other stories to go with it. Grayson?
Gotta go to Canada.
Yeah, that's right. All right. So that's that one. So remember again, it's y over x, so that's the 9 over 5. All right. Now sometimes you guys, and this is something you learned in Math 7, you can have a straight line, so it's linear when you graph it, but it's not proportional. So I'm going to talk about that right now. This is a little 7th grade math. So you have something like this. I'll let you write it down and then we'll talk about it. Basically it says the graph will be linear but not proportional of this. Question?
The 0 on the example 2, like, will be 0 times 5, or, like, how does it become 5?
That's actually how it's changing. If it goes up 5 degrees, then it'll be a 41 Fahrenheit. Those are actual temperatures. So here, you guys, we have a linear graph. If I'm going to graph it, I'm going to get a straight line because I get 9/5 every time, right? But it's not proportional because if I take the y's and put them over the x's, like 41 over 5, I get 8.2. And if I put 50 over 10, I get 5. And if I put 59 over 15, I get around 3.9. See, I'm getting different numbers with my ratios, right? So that means it's still a straight line, but it's not proportional. And I'm going to go back to 7th grade and stretch your brain in just a minute. But since the ratios are not the same, the relationship between Fahrenheit and Celsius is not proportional. On your homework, you're going to be asked to find the rate, and then you're going to be asked if it's proportional or not, and why.
And they hear you, Michael.
That's why I stand here.
No, some notes
So I'm guessing they can.
Okay, so 7th grade people, they remember 7th grade. Here's my question for you. In 7th grade, you learned to look at a graph, and just by looking at it, you could say whether it was proportional or not. And there was 2 conditions for it to be proportional. 2 things the graph had to look a certain way. Raise your hand if you remember. 2 things for a graph to be proportional. Tanner?
The line has to be straight.
Straight, and Ryan?
It has to go through 0.
Through 0.
0.
Good. You remember. You must have had a good Math 7 teacher.
I know.
So the line had to be straight, and it had to go through the origin, which is 0, 0. Remember the origin? It's the center. So for it to be proportional, it has to be linear or straight and go through the origin, either going up for positive or down for negative. But it has to go through the origin to be proportional. Okay, and later on I'll explain why when we get to that day. Right? But for now, take my word for it. In 7th grade you might have learned a little bit. There's a proof and there's a reason why. But some of you are already thinking ahead like, oh, it has to start at 0. Maybe. It doesn't have to start there, but it has to go through there. Okay, any questions on proportional, linear? It's a little bit from 7th grade still, so these words should be kind of familiar, right? Hopefully.
Nope.
All right, next page here. All right, so sometimes you're given a graph. Those were tables. Now we have a graph. And in this graph, let's just say this is a mountaintop at 6,000 feet and we're hiking down, okay? So this one's going down. So we already know it's going to be negative slope, right? It's negative when you go down. And the question would be, is this graph linear? You can tell by looking at it that it's linear, right?
No, because it's not going to the origin.
No, that's proportional.
Ha ha ha.
Straight line means linear. But we can check anyway. We can check. We can plug in some values. I have a 6,000. At 6,000, I'm at 0 for x. You see y is 6,000. At 4,000 feet, I'm at 2. And at 2,000 feet, I'm at 6. So I just divide that out. And it's negative 2,000 over 2 every time. It's going down 2,000 and going over 2, right? Going down 2,000 over 2. So that's constant. So that makes this linear, constant linear.
And so it's linear if it stays like.
Okay? So it's the same rate of change every time.
But it does not have to go through the origin.
Right, so it's not proportional. Doesn't go through the origin. But it is linear, has the same rate of change. Emma?
Is that like half a graph?
No, that could be a graph. If you started at 6,000 feet and maybe you walked 6 hours and after 6 hours you're at the bottom of the hiking trail or something, right?
Who does that?
Okay. Maybe you prefer to jump out of an airplane and after 6 minutes you're at the ground. Either way, you're going down. You need to think down and to the right is negative, right?
How do you know that's
Okay.
going down?
Well, you start at 6,000 and it goes down to 0.
What if it starts at 6 and goes?
Because then it'd be going backwards, and backwards is negative, isn't it?
Oh yeah.
Yeah? Okay. Not literal mountain, but think like a graph and how graphs are. When we go to the left on a number line, we're going negative, right? Good questions. So yes, this is linear. If it asked you after that, the next question, like on your homework and the practice, it will say, is it proportional? Then you would say no, because it doesn't go through the origin. But linear, yes indeed. Any questions on that? So again, it's just the y over the x, the y over the x. Think constantly, the y over the x. And there's formulas and there's all these things, but a lot of you will just see the tricks like that. You'll just be like, oh, y over x, and divide or whatever you need to do. Okay? We'll get better at it. All right, so what we're going to do before we do the second set of notes is we're actually going to practice some of these. And in your book, you're going to do page 175, 1 through 7. So turn there, and then I will go over some of those problems first before you start.